Hey, research methods. This is Dr. Gilchrist, and we are working through Chapter 5, going through talking about how to calculate a confidence interval when we know sigma. So one of the things that I did want to mention that your book also talks about, if you go to page 102, they do show you the equation for a margin of error, which is 1.96 times the standard error. Now, as you will remember, 1.96 corresponds to 95% under the curve of a normal distribution. So this corresponds to the z-score of a distribution that accounts for 95% of the data. And then we have our standard error, which takes into account the standard deviation and the variability of our sampling distribution. So our margin of error helps us figure out 95% of where the data is under our sampling distribution. So if we know sigma, we can calculate our margin of error the way that you see here. So one of the things I will mention is that your confidence interval is basically going to capture your margin of error both above and below your point estimate. A margin of error is 1/2 of your confidence interval. So here, to calculate a confidence interval using sigma, so when you know sigma, you take the mean minus your margin of error, and then the mean plus the margin of error. Now, one thing your book mentions on page 102 is generally for eyeballing purposes, you can round up 1.96 to 2. It's not going to be perfectly accurate, but for eyeballing purposes, it'll give you a pretty good feel for that. So this is going to give us a 95% confidence interval because a z-score of 1.96 accounts for 95% of the area that is under a normal distribution. And in psychology, many of the things that we are trying to study are also normally distributed. And this 95% is what we are going to refer to as a level of confidence. So let's talk a little bit more about this level of confidence. So we call it the level of confidence because this helps us figure out how confident we can actually be that our confidence interval includes mu, the mean of our population distribution. And generally what we are going to find is that researchers are often going to pick a 95% confidence interval. Generally, 95% confidence is pretty darn good for most intents and purposes. Now, their other values are kind of possible. You're always more than welcome to mess around with those with Esky. So for example, if I wanted to look at a 99% confidence interval, you would actually want to replace this 1.96 with 2.58. That is the z-score that corresponds to 99% of the area under a normal curve. So 95% of the area under the normal distribution is going to be accounted for in your confidence interval, but we can actually vary what our level of confidence is. So this is generally going to be a matter of personal judgment and what you're looking for. Do you want to have more certainty that a confidence interval actually does contain mu? If that's the case, you might want to choose a 99% confidence interval. Additionally, would you like a narrower range of values? In that case, pick a higher level of confidence, or a wider range of values, pick a lower level of confidence. So changing your confidence, changing C, our level of confidence, ultimately changes our confidence that the confidence interval itself contains mu. So one of the things that you'll note, we selected the value for 95% levels of confidence by consulting our Z distribution. So you can kind of think of 1.96, the Z-score, as Z95, the Z-score for 95 over 100. So based on our level of confidence, we can actually change our formula for a confidence interval when we know sigma to the Z-score associated with a certain level of confidence. So for example, as I mentioned, if you want a 99% confidence interval, that Z-score is going to be 2.58 rather than 1.96. So this is a very general formula for a confidence interval when you know sigma. So finding different levels of confidence means you're going to have to go back to that Z distribution. Now, I've already, I can pull up some of them for you. You can check your Z distribution and you can actually test some numbers here. So as I mentioned, a 95% confidence interval requires 1.96. A 99% confidence interval requires a Z-score of 2.58. So really quick, we're going to go into Esky and we're going to test a few of these numbers so that you can kind of get a feel for what they are. So if we go to our normal distribution here, and we want a certain Z-score, and I'm going to move my head here. So let's say that we were looking for a 90% confidence interval. What would our Z-score be in this case? So I'm going to focus on this little percentage right here where most of the data is. And then once I know that we're at 94% for this data, I can look at the Z-scores reported here for each of the tails to figure out what that critical level of confidence Z-score is going to be. So I'm going to go ahead and scroll. So obviously we're going to want a smaller confidence interval here. So I'm going to go ahead and move the cursor myself because this is going to take a while. So here's our confidence interval. This is about 9. So we're really close here. So we're at about 91% confidence. Here's 94, 91. I'm going to go ahead and stop it here. Oh, that's 85. We don't want that. I'm going to go ahead and move this up a little bit. We're going to scroll. We're going to scroll. As you can see, this can take a while if you're playing around, which I am because I like to. So we're going to keep going. So right now we're at 1.59. Oh, it's broken and it's not stopping. Okay, so now I'm at 1.6 and I'm at about 0.89. So we're dangerously close here. So we're going to keep scrolling and scrolling. There's a little bit of noise going on in the art gallery, so hopefully it won't really throw me off talking. As you can kind of see here, we are getting dangerously close to that 90% under the curve. Oh, I didn't want that. Okay, we need to go down a little bit. So we're going to go down, down. Oh, we're so close. Oh, so close. Okay, please stop. All right, here we go. 91.2, 91.5, 89.5. Okay, so it's kind of clear here that our critical Z is probably going to be around 1.6 when you're messing around with this. And so hopefully you can kind of look through that and get a pretty good idea of the different Z-scores that you would need to be able to do this. And by the way, when you figure out that Z-score for your level of confidence, when you figure out that Z-score, not only does it work for your confidence interval, so it'll be for example, a 90% confidence interval. So once you figure out that Z-score, you then can also plug that into your margin of error. So hopefully this will kind of help you out a bit. So now we're going to move on to an activity. We are going to talk about the dance of the confidence intervals. So once again, I am going to go into Esky and I'm going to kind of walk you through this in this case. So the dance of the confidence intervals, we're going to want to go ahead and go to, once again, our CI jumping. So we're going to go to our CI jumping here. So you can follow along. Directions are also provided in your book. So hopefully this will help you out. We're going to go ahead and keep our population as a mu of 50 and a sigma of 20. Okay, now I'm putting in headphones to block out the noise because I need to be able to focus, and I kind of can't focus when there's a lot of noise going on in the hallway. So you can follow along in page 103 of your textbook to kind of get a feel for how this works. So we're going to start with our normal parameters of a mu of 50 and a sigma of 20, and we're going to go ahead and fill in random. We're going to go ahead and have a sample size of 20. We're going to go ahead and do our sample means and our dropping means. But here's what's kind of critical. So now we're going to assume that sigma is known. We're going to go ahead and set our confidence interval to 95. And additionally, we're going to click CIs. So we've got that in 6. And then in number 5, we're going to have our mean heap. We want to put our margin of error around mu. And so actually I kind of got this messed up. So let's go back a little bit. We aren't going to start with the CIs. We're going to start with a sample of 15. And we're just going to really quickly take a look to see how many of these means are actually going to fall outside of that margin of error. So I'm going to go ahead and start running this, and we're going to see how many of these dropping means fall outside of our margin of error. So far, so good. Very few of these means that we're getting from these samples, and remember our sample size is 15, very few of these are going to fall outside of the margin of error. In this particular instance, we do see at least one that is right on the border. But so far, most of our data is actually falling within those lines. So we'll just kind of watch a few more, and I would encourage you to try this yourself. And again, the directions for this are on page 103 of your textbook. Okay, so there's another one that we have. I'm going to go ahead and stop me. And it did stop. And you can see that we took about 25 samples. Really, only about 2 of our repeated samples fell outside of our margin of error. And so that kind of fits with this notion that our margin of error for a certain level of confidence is going to capture that the bulk of where our data is. So because we're using a 95% confidence level here, we can be pretty sure that our margin of error is capturing about 95% of the data in this sampling distribution. So as 5.7 says, the green stripe at the bottom has the length of 2 times the margin of error. So basically what we are going to do at this point is we are going to click on assume that our sigma is known. And this time we're going to do CIs. And so what I have actually done is now you can actually see the 95% confidence intervals for each of our sample means. Now, what I want you to kind of notice based on the ones that we've taken here is that while most of our means fall perfectly within the margin of error, notice that considerably more of our 95% confidence intervals do have components that fall outside of our margin of error. So I'm going to go ahead and clear this. And we're going to go ahead and we are going to run the dance of the CIs. So we're going to watch a few of these and we're going to go ahead and run them so you can see the confidence intervals fall. So note that most of these will have means that perfectly fall, the means, our sample means, are going to fall within that margin of error length. But notice that sometimes the confidence intervals, even for ones like this one, that are right with a mean that's falling within our margin of error, has a confidence interval that extends outside of the margin of error. So we're just going to watch a few of these and see what happens. So notice again that very few of our data points, our sample means, are falling outside of that margin of error. Now there are a couple that are. We have a couple that are just right touching the border. So now we're going to look at another instance. So now we're going to look at every time that mu falls within one of our confidence intervals. So our mu is 50 here. The most recent sample mean was 52, and so that's right here, and its confidence interval actually captures mu. So now we're going to move to 5.8. So here, a confidence interval that includes mu or captures mu every time unless the sample mean actually falls outside of the margin of error. So now we're going to go ahead and we are going to run another simulation. So I'm going to have a line for mu, and I'm going to indicate how many times something actually captures mu. Now, based on the most recent sample that I took, what you're going to see here is that ones that have sample means that fall outside of the margin of error do not capture mu. Anything that has a sample mean that falls within those margin of error lines, even if the confidence interval extends outside of those lines, will capture mu. Notice that the edge of the confidence interval here, for example, does actually capture mu. So this line is where mu is, and you can see that's indicated right here. So now I'm going to go ahead and clear. And we're going to run a lot of different samples. And what I want you to kind of pay attention to once I'm done taking a significant amount of samples is we're going to figure out how many samples captured mu and the percent of those samples that captured mu. So we're going to go ahead and run this for a few minutes. I'm going to pause this and let this run. And when we're done, we'll go back and take a look at it. Okay, so I just put it back on record. I took 132 samples. You can actually see 2 of our confidence intervals failed to capture mu because their sample means fell outside of our margin of error lines. So I took about 123 samples, and you'll notice that it's not quite at our 95% confidence interval, but over 93% of the samples that I took ended up capturing mu. That's a pretty sizable portion, and if I had more time to take more samples, your book suggests like hopping on Esky, kind of setting this up, and kind of running it over a long period of time, like 10 minutes or even an hour, to kind of see how close the percentage that captures mu approximates that level of confidence. I would also encourage you, this is with a sample of 15. One of the things that we're going to find if we get a smaller sample size or a very small sample size, so I'm going to go ahead and pick a sample of 4. I'm going to clear. I'm just going to take a couple of samples, and what you're going to notice is that compared to previous, notice that our margin of error lines have gotten larger, and additionally, so have our confidence intervals. If I clear this, and I have 100 people in my sample, so I'm going to go ahead and take a sample. Notice that my margin of error lines have gotten much, much smaller, as have my confidence intervals. Now, that doesn't mean that sometimes you will have a value that does not capture mu. So if I ran this enough, I would eventually get a sample mean that falls outside of this margin of error. But my level, my confidence interval has shrunk, and now there is a greater opportunity here to actually end up capturing mu as a result. So I'd encourage you to try this out. So now let's kind of talk about this a little bit. So we did the dance of the means, and everything that I have just done for you is what we call the dance of the confidence intervals. So this can tell us about the value of mu. Now, random sampling does mean that most of our sample means will not actually equal mu, but they will be captured by most of our confidence intervals. So most of our samples will have mu falling within the confidence interval. Here in this example, you can see 2 that do not. And this is also based on a sample size of 15. Some confidence intervals are going to fail to capture mu, and that's because we never have 100% certainty. So now we're going to move on and talk about the t-distribution. So we have been doing all of this with the idea that sigma is known. But most of the time, sigma is not known. So most of the time, we don't know sigma. So just as we use a sample mean to approximate the population mean, mu, we are going to use our sample standard deviation to serve as a proxy for sigma. So our best information about sigma is going to be in the standard deviation of our sample. But if you want to calculate a z-score, that's based on a normal distribution. That's only going to work if you know sigma. So now we're going to have to talk about using the t-distribution. So what you are looking at here is the normal distribution in blue and the t-distribution for in red. And what you're going to notice is that we're going to have to calculate a different score for 95% under the curve. So this is with 14 degrees of freedom. We'll talk about what that means in a minute. And the cursors are set to t being plus or minus 2.145. This provides 95% of the data. Now, what's really important here, remember how I mentioned that 1.96 is the z-score that always accounts for 95% of the area under the curve? That's always going to be the case for a normal distribution. In the case of a t-distribution, you are not necessarily going to have the same t number every time. And we'll talk about why that is. So a 95% t-score for 14 degrees of freedom is 2.145. So the t-distribution, as you can kind of see, is really similar to the normal distribution. So even without finding sigma, we can get 95% of the data under the curve. But the t-distribution and the critical value that you need depends on degrees of freedom here, which is something that we did not need when we know sigma and we can use z-scores. So I want you to kind of remember how to calculate z-scores. So really quick, this is kind of a weird way to kind of think about it, but really, here's a z-score. So remember that a z-score is a value minus the mean over the standard deviation. Now, when we talk about this in terms of a sampling distribution, now it's our particular sample mean minus the mean of the population. So we have our estimation error, and then we have the standard deviation of our sampling distribution, which is our standard error. So this is just another way that we can think about calculating z-scores. We take our sample mean minus the population mean and put all of that over the standard error. It's just a way to do x minus m over standard deviation for a sampling distribution. Now, we are going to substitute our standard deviation in place of our sigma. We still get the same result, we just replace our standard deviation over sigma, and that will help us figure out our t. But it's a lot harder for us to find a t-distribution, and note that it says a distribution, not the. Now, that's because there is a t-distribution for every possible degree of freedom that you can have, or every sample size that you have. So this is where degrees of freedom comes in. Don't panic if you don't understand this right away. First of all, I'm happy to explain it to you, and at some point, this is going to click for you. Just make sure that you know how to calculate it for now. Your degrees of freedom are your sample size minus 1. When I get to class next Tuesday, I will kind of show you the logic behind degrees of freedom and why it's n minus 1. But for right now, you just need to know what it is. It's the number of people in your sample minus 1. So what are degrees of freedom? So degrees of freedom are the number of separate independent pieces of information that you need related to the question at hand. So if I'm thinking of 4 numbers with a mean of 7, what this means, if I give you 1 number, you still don't know the other 3. If I give you 2, you won't know the other 2. But if I give you 3 numbers, n minus 1, I already know what the last number has to be, because now that I know what the last number has to be, knowing all 4 numbers doesn't give us any new information. All we need is 3 minus 1. If we know everything except the last one, we by nature have to then know what the last one is. And we'll kind of talk about that more on Tuesday. So in this example here, with 4 numbers with a mean of 7, our degrees of freedom is going to be 3, which is the same as degrees of freedom equaling our total number, 4 minus 1. So in the context of calculating our t statistic from a t distribution, degrees of freedom is going to tell us the number of independent pieces of information that our standard deviation offers. So generally what we're going to find is that larger degrees of freedom means larger n, and the larger that our degrees of freedom are, the more closely t approximates our normal distribution. And if you want to see this for sure, you can actually check this out in Esky. So if I go to the normal and t distribution, so here's my normal distribution, and then I also am going to put my t distribution on that. I'm going to go ahead and put, so you can kind of see that there's some difference here between the two. Now, notice if I put 5 degree, don't say that to me, don't talk to me like that. If I reduce my degrees of freedom by a bit, you're going to see more of a difference between the two. But if I increase this quite a bit, it won't let me do it. Okay, so what I'm going to have to do here is I'm just going to have to hit this slider. So I'm just going to let this run for a second. So if we get to, for example, like 50, notice how much more they approximate. The higher the number, the more closely my t distribution is going to approximate my normal distribution. So here's what you need to know about degrees of freedom. In general, bigger is better. Our degrees of freedom is calculated as the number of participants in our sample minus 1. And knowing your degrees of freedom is going to help you figure out which t distribution you need when you're trying to find that critical t statistic, that value you need. Try to understand what degrees of freedom represent, but it's okay if you don't. Sometimes it takes running through it and thinking about it more than once to be able to understand what it means. So now let's talk about how to calculate a confidence interval when you don't know sigma. And generally, you might as well get used to it, because most of the time as a researcher, you are never going to know sigma. So knowing how to calculate a confidence interval using a t-value is really important. So remember that when we know sigma, our formula works like this. We have our mean minus the z-score associated with a certain level of confidence times our standard error, and then the same, but we add that margin of error. So now all we're going to do is we're going to substitute t and standard deviation in place of sigma, but it's basically the same idea. We have a t statistic for a certain level of confidence and with a certain degree of freedom times our standard error, and then the same for the upper bound. And again, as we saw before, if it works for a confidence interval, it works for our margin of error as well. For 95% confidence intervals, our margin of error will be our t statistic at 95% confidence with a certain degrees of freedom times our standard error. So now I'm going to finish up by doing one more confidence interval, and this time we are not going to know sigma. So I'm going to go back into confidence interval jumping. I'm going to go ahead and clear this data. And as the figure kind of suggests, I'm going to go ahead and I'm going to do exactly what we had before. So we're going to have our population value, our population mean of 50 and our sigma of 20. I am going to go ahead and do 15 in our sample. So that's 15 in our sample. I am going to assume that sigma is not known. So I want you to kind of watch what happens when I do this. So one thing I want you to kind of notice, when you know sigma, all of the confidence intervals have the exact same length. When you don't know sigma, I want you to notice that the confidence interval sizes start to vary. So in this particular instance, when you are calculating our confidence intervals using a standard deviation rather than sigma, the dance of the confidence intervals changes. So here's what it looks like when we know sigma. Notice that the confidence intervals are the same length. Most of them will capture mu, but when you don't know sigma, notice that the confidence intervals vary in length from sample to sample to sample. So you're going to be more dependent on standard deviation, and that's going to vary based on your sample size. So I went a little over 30 minutes. We will talk about this more next time, and I will see you then. Bye.